Good morning, everyone. I am Meghana, an electronics and communication engineering student. Today, I am going to present my internship project titled Development of an EV dashboard with ADAS features using STM32 microcontroller board and Python, completed during my embedded systems internship at MXG Information Technologies under the guidance of Jay Lakshmi ma'am. The main objective of this project was to develop a real-time electric vehicle dashboard capable of displaying vehicle parameters while integrating basic ADAS features to improve driver safety. In this presentation, I will first introduce electric vehicles and advanced driver assistance systems. Then I will move to objectives of the project, followed by overall system architecture, and finally I will demonstrate the project results. The main objective of this intensive project was to develop a real-time EV dashboard capable of displaying important vehicle parameters. The dashboard monitors vehicle speed, battery, SOC, battery temperature and brake status and motor torque. Along with monitoring vehicle parameters, another objective was to integrate basic ADAS features. These ADAS features include forward collision warning and blind spot detection. An electric vehicle is commonly known as EV, uses electric motors instead of internal combustion engines. Unlike conventional vehicles that depend on petrol or diesel, EVs are powered by rechargeable battery packs. This battery management continuously monitors battery health and ensures safe charging and discharging. Modern EV dashboards are becoming smarter by integrating intelligent monitoring systems and safety features. Coming to ADAS, which is also known as Advanced Driver Assistance System. This system assists drivers by continuously monitoring the surroundings using various sensors such as ultrasonic sensors, cameras, and radars. The primary goal of ADAS is to reduce accidents caused by human errors. In our project, we implemented forward collision warning and blind spot detection using ultrasonic sensors. Whenever an obstacle enters the defined safety zone, the system immediately alerts the driver through the dashboard. Now, coming to system architecture, which gives the complete idea of this project. The system begins with two types of inputs. The first input is obtained from the potentiometer. As we are doing simulation right now, real world sensors can't be used. So we used potentiometers, vehicle parameters to find, such as battery, motor torque, and speed. The second input comes from the ultrasonic sensors for the ADAS features. All the sensor data is sent to the Blue Pill STM32 microcontroller board. This microcontroller board processes the received data, executes the EV dashboard logic, and implements the ADAS algorithms. The processed information is transmitted through UART communication to the computer. Finally, the Python dashboard receives the data and displays vehicle parameters along with the safety alerts in real time. The hardware components we have used here is the STM32 Blue Pill board for processing the information, which is heart of the project, and the ultrasonic sensors, which ranges from 2 centimeters to 400 centimeters, uh, used in ADAS features, and the potentiometer, which acts as a real-world sensors to find the current sensor values like temperature, motor torque, speed, and finally UART for communication between the controllers and the dashboard. Let's move on to the software tools. The software tools we have used during the development is STM32 CubeID used to write, compile, and debug the software firmware. And Pixim Lab used provide virtual hardware environment for testing. And next, Python used to design the graphical dashboard that displays vehicle information. And VSPE, Virtual Serial Port Emulator, created virtual COM ports to establish the serial communication. And finally, Teratom was used to monitor UART data during debugging and testing. And coming to the working methodology, the project follows a sequential workflow. Initially, potentiometers simulate vehicle parameters while ultrasonic sensors continuously detects nearby obstacles. And next, STM32 acquires these inputs and processes them according to predefined algorithms. The ADAS logic determines whether the warning conditions exist or not. The processed information is then transmitted through UART. Python continuously reads incoming serial data and updates the dashboard. Whenever unsafe conditions are detected, corresponding warnings are displayed immediately. Our dashboard provides real-time visualization of EV features like speed, battery, brake status, and temperature and motor torque. And the first ADAS features implemented in is forward collision warning. The front ultrasonic sensor continuously measures the distance between the vehicle and the nearby obstacles. Whenever the obstacle enters the predefined safety threshold, dashboard immediately displays a warning. The second feature is blind spot detection. Separate ultrasonic sensor monitor the left and the right blind spots. If another vehicle or obstacle enters these regions, warning indications appears on the dashboard. The system also performs fault detection by identifying abnormal conditions. Before implementing the project on actual hardware, the entire system was tested in the Pixim lab, which simulates the STM32 blue pill board along with the ultrasonic sensors and potentiometers. Changing the potentiometer values simulates changes in speed, SOC, brake position, temperature. Obstacle detects generated by the ultrasonic sensors or processed by the blue pill board. And the below what are the terminal results which we found out. And next, the project was successfully executed in the simulation environment, which is a Python dashboard. All EV parameters and the ADAS features are shown in this picture. And let me show you the demonstration of the video. Now, this acts as a potentiometers. And this acts as a potentiometers, and these three are the ultrasonic sensors which detected to forward collision, and these two are the blind spot detection ultrasonic sensors. And this is the acceleration pedal, and this is the brake pedal, and this is the SOC, and this is the temperature potentiometer. Let's see the outputs on that virtual terminal. ఏదో ఒకటి అప్లోడ్ చేసేద్దాం టైం అయిపోతుంది